Our next item we're going to talk about, I need to preface with telling you something now. Before you disagree with me, before you send me a bunch of nasty emails, before you throw something at your monitor, okay? Please listen and I will give you evidence to back this up. The universe as we know it is not perfect. I know, most of you probably disagree with me. But evidence of that is all around us. Next we're going to cover isotopes. The prefix iso means the same. And you should write that down the margin of your paper. Iso means the same. Now, in the universe, we talk about atoms. Where atoms come from is actually inside of stars. There are protons, electrons, and these bundles of energy we call neutrons are formed, and they come together to form a hydrogen, and then two of those come together to form helium. You add another hydrogen, you have lithium, and all the elements build up bigger and bigger and bigger. And we said, rule of thumb is the number of neutrons should equal number of protons. There is one sweet number for the number of neutrons that should stabilize that nucleus. And most of the atoms have that number. However, nature sometimes makes mistakes. It's kind of like a recipe. If you're making, not an atom, but let's say I'm kind of known for my chocolate mousse at TVCC. So I bring it to a party and everybody loves it, and so we're going to have another retirement party, and they say, well, bring the mousse, and well, I just made mousse, and we don't care, bring mousse. And I'm at home making mousse for the retirement party, and my son calls me up and he says, what are you doing? I said, well, I'm making mousse. And he said, well, okay, so you're making some extra and you're going to bring it to my brother and I. And I said, well, I really wasn't planning on that. Well, come on, you're making mousse, you got to make us some. Okay, fine. So I started making them some, I'll make another batch. The first batch, I tried it. Tastes really good. Put the same amount of sugar and butter and eggs and everything in it. And the second batch tastes pretty much like the first one. Tastes good. Then my ex calls me up and says, hey, boys tell me you're making mousse. You make some for me and my family? Kind of odd. I don't think she understands the concept of ex-wife. Well, we love your mousse, and we'd like to have some mousse, and you can drop it off. And reluctantly, I say okay, and I put the same amount of salt and chocolate and eggs and everything, and I make it, and somehow though it ends up being horrific. Oh yeah, I think I forgot the sugar, and so they don't ask me for mousse anymore. Kind of solves the problem. But again, where nature doesn't always make the recipe the same. Now, if nature changes the number of protons, you change the element. You can't change the number of electrons because atoms are neutral, so they have to equal the number of protons. But what can change is the number of neutrons. And that's where you get isotopes. Same element, but with a different number of neutrons. And remember, neutrons control two things. One is the mass, the atomic mass of the atom, and also the stability. So same element, different number of neutrons, different atomic weight or mass, and also stability. One of the most popular series in chemistry is the carbon series. Here on the left we have carbon, of course, atomic number 6, so there's 6 protons in here. A rule of thumb says the stable one should be the one with 6 neutrons, and here we have 6 neutrons, so the atomic weight is 12. And of course, a neutral atom has to have 6 electrons, and we do 2 in the first shell and 4 in the second shell. Nature sometimes makes a little mistake and puts in extra neutron. So that creates what we call carbon-13. Has an extra little neutron in here. Still has 6 protons, 6 electrons, but now 7 neutrons. It's a little bit heavier, and it's not quite as stable. Even too much glue can be a bad thing. And the most famous one is actually carbon-14. This one has way too much glue. It has 2 extra neutrons, and it makes it unstable. So it falls apart somewhat readily. Okay, not in our lifetime, but considering the universe. When it does come apart, it's called radioactive decay. Decay means it's going to fall apart into two or more particles. And radioactive has to do with the particles it will give off, and those with energy. What we expect to happen is something like this. Now, I'm taking some poetic license on this because I don't want to show you a bunch of different examples, or I don't want to show you something like uranium that would be way too complex to build or to manipulate or follow. So I'm taking some liberties on these. We expect for a bigger particle to go down into two or more smaller particles, right? Now there's three different types of radiation we'll talk about. Alpha radiation. Now alpha, beta, and gamma. All that means in Greek is A, B, C, or 1, 2, 3. This is the lowest level of radiation. Particle comes off of there that's basically a helium nucleus. 2 protons and 2 neutrons. So of course our main particle is going to get smaller. When this comes off, this alpha radiation, it's low energy and it's using all its energy to move. Subatomically, this is pretty big. It's like a semi-truck. So it also has size and mass, which means when it hits something, it's pretty much going to stop. We have pellets in the lab that we use to study radioactivity, and they give off these radioactive particles, these little chips. Now you take one of those out and it's giving off these alpha particles. If you want to save yourself, well, you don't have to worry about alpha radiation. When it hits your clothing, it stops. When it hits your dead skin on the outside, it stops. If you want to save everybody in the room, put this in a paper bag, because literally it cannot fight its way through a paper bag. So these usually not a problem. Now, I used to always joke, well, I wouldn't eat 5 pounds of this. Really, I wouldn't eat any of it. Alpha particles will be stopped by dead tissue on the outside. But if you consume alpha emitters on the inside, now they come in contact with living tissue. And they can affect you. And in fact, they can cause cancer. As they found out, they sampled water wells across the United States. And they found that over 1,000 wells had alpha emitters in them. And if you drink these, of course, you can get different types of cancer in your GI tract. So not good. So they shut down the water wells, or they had to filter out the particles. Now beta, this is weird. This is one of these weird things in science and nature. A beta particle is actually a neutron that changes into a proton electron. The electron comes zipping out, as you saw. But that actually means that this thing goes up in atomic number. Atomic weight stays the same, but atomic number actually increases. So this thing literally gets bigger, which is sort of the opposite of what we said in the beginning. About 5 elements actually do this. Weird, freaky things in nature. Now the electron, though, remember, has a lot less mass. So it can travel a lot faster, and it can cause more trouble. It might be able to penetrate through your shirt, a little bit through your skin. So, hey, you want to be totally protected, put up a piece of plastic. This cannot fight its way out of a plastic lunchbox. And you'll stop it. Of course, the most famous one is gamma radiation. High bundle of energy, just less than a neutron, but has a lot of energy and it's approaching mass. You can get a lot of chemical reactions that normally do not occur if you add in a high amount of energy. And that's what this releases, just a bundle of energy. And it's kind of like a little lightning bolt. When I was a kid, one summer, 3 times, electrical lines out front of our house at the corner, the insulator overheated and broke, releasing the electric cable into the front yard. The first time they came out, they said there was some 30,000 volts going through that. Of course, high up on the telephone pole, electric pole. Later on in the summer, did it again, and they said there was like 50,000 volts. And at the end of the summer, a lot more people were coming out, and they were hooking up a lot more electricity, and they're pumping a lot more electricity through the wire. one early morning, the insulator broke and dropped in the front yard, and you could see not only the electricity surging into the ground, but also the dew on the grass was just electrified. And so we walked outside and saw it. My brother's like, "Oh, we'll go out in the front yard." I'm not going out there. I'm not stupid. So we called the electric company, and they came. They shut it off. They put it back up. And they said, "Well, we put a reinforced insulator in there. It shouldn't really break, but the equivalent of 100,000 volts going through there." 100,000 volts. Well, we had to upgrade a lot lately, and it should be able to handle it, but they reinforced it. Never had a problem after that. So for about 20 or 30 minutes, there was all these volts going into the ground. And they said, "Well, we killed your grass, but just dig up the dead grass, plant some new one, send us a bill for $5 for grass seed." And of course, that was my job. So I go out in the front yard with a shovel, and I go to dig up the grass, and I hit it, and I hear this tink. I hit rock. We don't have any rocks in the yard. So I move back a couple inches, and tink. What the heck's going on? I move back a couple more inches, tink. Something's going on here. So I get down on my hands and knees, and I pull the grass off. And underneath is this huge green glass egg. It was egg shaped. If you ever saw the movie Sweet Home Alabama, talking about lightning hitting the sand at the beach and it makes these beautiful sculptures. No, it doesn't. After that movie, a lot of people got in accidents. Even I think one got hit by lightning because they're at the beach during the electrical storm trying to get these sculptures. That doesn't happen. But you put 100,000 volts to the ground for a half an hour, and it took the clay in our soil. Now, I'm from Pennsylvania. Our clay has more, it's more of a blue and gray clay than a red clay like iron down here in Texas. But it was like in a kiln, and so it changed the glass with a green and bluish tint from that clay, with little pockets of air bubbles and also dirt. It wasn't beautiful. It was ugly as heck, and nothing you could even sell on eBay. But this big, huge mound of glass. And if I took that clay and put it up on a rock in the sun, trying to get it to do the same thing, it probably wouldn't ever happen, because it would never get enough energy. So again, where you provide enough energy, you can get something to do that normally shouldn't do it. That's how gamma radiation, why it's such a problem, is because normally your DNA is a very stable structure to keep your blueprint, how to make you, how to keep you alive. Yet it gets hit by a bolt of lightning of gamma radiation, and it can twist it into another shape. And that creates a problem. You fix that problem, that causes perhaps a mutation. Mutation's a change in that blueprint. And if you can't maintain the directions for life, it can kill you. And so literally, well, figuratively, what happens, if you missed that, don't worry, no cats were actually hurt in this animation. Now, that gamma radiation is basically a bundle of energy. It can pass through the air without a problem. It can pass through your shirt, your skin, your flesh. Now, maybe if it hits a bone straight on or something like lead, and that's why lead's, you want to protect yourself from a gamma emitter, put it in a lead box. Lead is very dense and will stop these particles from moving. Now, how fast they decay, that's measured in a unit we call half-life, the time needed for half of the isotope to decay. And so here we have a scale on the bottom, number of particles. Let's say whether you're talking about 100% or 100 particles, and randomly they're going to start falling apart. Notice when we get to half the number, that's one half-life. For carbon-14, its half-life is 5,730 years. After another half-life, we're down to 25. That would be 11,460 years. And we keep on going, but eventually it's going to wear out. Okay, from 25 we go down to 12 or 13. Math is easier with 12. Then 6, then 3, then 1 or 2, and then none. So it will end. And carbon-14, or what we call carbon dating, is not dating site for science geeks online. But that's another one of those jokes. But what you do is you take something like a bone we find out in the courtyard, a cow bone, and we want to know when old Bessie died. Now we know what the normal percentage is of carbon-14. It's something like 0.75%. Now, from that 100%, when Bessie died, she didn't eat any more carbon-14 to replace it. So this decay started, as we see here. What we do is we find out what percentage she has from normal, follow this curve over, and it would tell us how many years since she died. Now, of course, we can't use these for things like dinosaur bones because the scale's not big enough. We have to have enough of a drop. It's not accurate up here because we have to have enough of a decrease to actually determine the difference. And it's not accurate out here where there's very few particles left, or even, of course, when they're all gone. So for something like dinosaur bones are millions of years old, we'll use radioactive potassium that has a half-life of millions of years. For treating something like thyroid cancer, you use radioactive iodine 131, which just decays in a couple of days. That's its half-life. For genetic experiments, we use radioactive phosphorus, P32, which has a half-life of 2 weeks. And so we use particles appropriately. There are a lot of different isotopes out there, and we're learning how to use most of them for scientific purposes.